So today we're going to be talking a little bit about Conway's Law. Probably many of you are familiar with this concept already, but I'll give a real quick intro here that basically Conway's Law dictates that the things that you build are probably going to closely mirror the organization structure in which they were built. So I work at a company called Stored, where we're building what we call a cloud supply chain, so warehouses and logistics and that type of thing. We're a startup, and we have all of the cloud native stuff that you might expect, Kubernetes, Istio, whatever, all the things. And as we've been growing very quickly, we've added lots of people and services and code and teams. So with that quick overview of what Conway's Law is all about, I want to take us on a little journey here about how companies and organizations grow and how they organize over time and how their software is organized over time, and some of the tactics that we've used to both succeed and fail at being compliant with Conway's Law. So first, talking about growth, I was trying to get a little bit metaphysical and think like, okay, why do companies even grow, right? Like, there's this kind of theory that we probably all have in our minds where you start out as a small company, and then over time you grow and you like expand into different business verticals or different use cases for your customers. And the reason you want to do that is because you want to have revenue, right? Like your company probably wants to make money, and to do that you're going to need to have customers, and those customers are only going to come if you have useful features for them. But of course that's a very simple business model, and it's not sufficient. You need to have engineers in order to build those features, which contributes to expenses and detracts from your profit at the end of the day. And the more features you have, as we all know, the system gets bigger, and it's harder and harder to add new features, which is the meaning of that red arrow there, kind of detracting from useful features. But that's not quite enough, because the more engineers you have, the more coordination overhead you have, and then also as you're adding more engineers, you're probably adding management and just like other overhead, which all contributes to expenses. And the more coordination overhead you have, the less useful features you're going to be able to develop, just because of tech debt, organizational debt, whatever you want to call it. Things get more complicated. But there's also these useless features that you actually don't want, but who doesn't have a useless feature, right? Like you experiment, you try things, you don't know what you're going to need. You end up having useless features that your customers actually don't like, right? So this detracts from having customers at the end of the day. And it makes it harder and harder to build useful features. And the more coordination overhead you have, the more of those you're going to end up with. So in my mind, the only way to really deal with that is to have more clarity of vision. And there's sort of a vicious cycle there where the more useless things you have, the less clarity of vision you're going to have, and vice versa. But clarity of vision contributes to those useful features. But it detracts from coordination required, because the more clear you are about what you're trying to do, the less you need to talk between people about it. And then at the end of the day, though, your managers and your engineers detract from having that clarity of vision, because just the more brains you have, the less clarity you're going to have, because everybody has different opinions. So as you can see, this is a very simple business model. I'm sure it reflects everybody's company, right? Like you all already knew this. But let's talk a little bit about organization with that in mind. So probably many startups start this way. You got a couple of co-founders where one of them's like the nerd and one of them's like the business person, and they work on building this. It's like it's an MVP, like it does one thing. But then over time it gets bigger, and maybe you attract some investors, and then maybe you have enough money that you can hire a team, and you start like piling stuff into this ball of mud. And it only gets more interesting from there, right? You start to hire more people, you start to have more teams, your ball of mud becomes a little ridiculous. And at some point it's like, well, we have these two teams, right? We should probably have two things, so let's just divide it in half in the most logical way possible, just right down the middle. And then over time and with significant effort and way more than you expected, you do manage to get it into two pieces. It doesn't make any sense, but you have two pieces now. And then with significantly more people and more effort, maybe it sort of makes a little bit more sense right now. There's less lines between the boxes, so that's definitely better. But then at some point you just get so big that you don't worry about what's inside the boxes so much. You just like have more boxes and boxes within boxes, and maybe just a completely partitioned company in some logical way. So this is what your management executives see at the end of the day, and they're like, oh, cool, look what we've done. Like we have these two product verticals, right? And there's these microservices, and all the engineers are having a fun time in there. But there comes a time where as a company you need to decide. You're starting out in the middle here with the grimace emoji face. You got your team there, and you're trying to build your ball of mud. The default choice over time, you need to pick a strategy, right? Like, how are you going to move forward? So the default strategy is the bigger ball of mud. If you don't make a choice, this is probably the trap that you'll fall into, and I'm sure many of you are there today. The more people you add to this, Brooks's law will tell you that it's just going to be more grimacing. So a common pattern here is just to split it into smaller things, right? Like each team can struggle in their own little product vertical or whatever and synchronously call each other. And that's a pretty common pattern that people go with. Another pattern is this event-driven microservices thing where you have maybe a Kafka stream and you have events flying between the different services. At least that sort of partitions, what you have to worry about. There's just like one thing going in and out. And then this last one here I want to talk about, I feel like this doesn't get enough airtime, so I wanted to give it its own time slot. You don't have to have a giant ball of mud. You could have just a monolith that's like, well structured and you have some rules and it's basically microservices but without the HTTP. Just saying, like you could try it. So anyway, Stored didn't do that. What Stored did is the synchronous microservices with this thing that we call Stored client. And what that does is each of our microservices uses this same HTTP client to talk to the other services. And what that gave us is a way to leverage Conway's law because this team, one of our teams owns the Stored client, and that gives us sort of a backdoor monolith that we can sneak into the architecture because Stored client needs to understand what APIs are available in all the different services. And we can enforce contracts. We can kind of like get in there. And yeah, here's some of the stuff that we can do there. So we get all these things built into Stored client. We don't rely on each team building, retries and load shedding and distributed tracing into each of their services and getting it right. That's all built into the client that we're using. And the client kind of hides the HTTP semantics from each of the services. So you're kind of like acting like you're just making a, like a regular Elixir call, but you're actually making an HTTP call. And what that gives us is some of the consistency and leverage that you would normally get from a monolith, but with microservices architecture. But that's not the end of the story because anytime you have more than one database, you're going to end up having issues where you can't just open a transaction, do these three things, and close the transaction and get atomicity. So we ended up needing to have Sagas to organize these distributed transactions across microservices. We're using the Sage library for that. And I will talk a little bit more about how that went. So we're building cloud supply chain software. So if you've ever read a textbook about distributed systems, you've probably seen our architecture because it's orders and warehouses and inventory. It's an e-commerce thing, right? Like you've read about this already. Super easy, right? You just, you call from one to the other and then you're done. But in theory, if you're using these Sagas, you need to be able to roll things back if something fails along the way, right? If you can't allocate the inventory, then you need to roll back and you can't create the order either anymore because it's not allowed by a business rule. So normally you would need a Saga coordinator, all the brains are there, and maybe a team could own that and call all these other dumb microservices, right? But it turns out that each of those microservices can't really be that dumb because they need to be able to handle these actions idempotently because in a distributed system, you may have a network call that gets sent multiple times due to retries or whatnot. So if this action has already been called, then it needs to know that it's already been called so that we can ignore that action from happening multiple times. Additionally, something that's not intuitive when you're using Sagas is that you also need these compensating actions for each of those actions that are also idempotent, but when they're applied after an action, they kind of combine as if that action had never happened. But again, they have to be idempotent because if any of these things happen again, you have to continue to ignore them forever. It's also possible that you can get the compensation action first. And in that case, if you later receive the action that would have happened, that has to work the same as if they had come in the normal order. So anyway, that's all just a warning about like, hey, Sagas aren't that easy. You should probably, not base your Sagas on just this conference talk. But one of the warnings that I do want to give you that we learned the hard way is that the Saga pattern can only be used to track business logic errors, not technical errors. So what that means is you can use the Saga pattern to roll back if inventory is not available as a business rule. So I might want to roll back, you can't create this order because we don't have enough inventory. But if you call the inventory service and it just times out and your process crashes and exits or whatever, then your state's just going to be, like your Saga is just going to be in an invalid state forever at that point. And you have to have a way to deal with that. So anyway, I don't have much time to talk about it, but I left a link here that you should read later if you're trying to implement Sagas or maybe this will convince you that you shouldn't try to implement Sagas, which is where I'm at with them now. Because we didn't implement that Saga coordinator, we actually implemented multiple Saga coordinators in each of the services where a Saga was needed, and it led to all kinds of disasters that are not fun to deal with. So the next step that we're looking at as a company is using this event-driven microservices approach, which I would recommend this book if you're heading down that path. But if you're too cheap for that book, you can go to this URL, and Confluent will give you a free ebook, which is almost as good, but it doesn't give you quite as much practical application advice. So it's more of an intro. And then while we're talking about it, I also recommend that you read this book if you're doing anything with distributed systems at all, independent of event-driven ones. And just as a quick aside, if you're thinking to yourself, I don't want to read 3 books, I just want to build a distributed system, I will give you the warning, do not, reading 3 books is the easy part of a distributed system. So just maybe you don't need to have a distributed system if that's your concern. They make really big boxes these days. You can probably fit it all in one. So anyway, yeah, this event-driven microservices approach that we're heading for now, the first step we decided to take there is using this event outbox approach, which you can read about in the book that I linked there. But this is a way that we figured we can bootstrap these events so that other services can start to consume those events before we're able to start consuming our own events. Because no one's sending these events yet. You have to bootstrap this somehow. So the way that works is we have this existing inventory service that has an HTTP API, like you might expect, just a boring old service. The goal here is that we want to have these fact events get published out into Kafka that other services can consume. And just, so you know what we're talking about, basically this is the inventory service is saying we have this many of this thing and it's in this facility. But another kind of optimization step that we have here is that each of these different colors represents a different customer partition where it doesn't matter the order of those facts happening because they're independent of each other. It's kind of like a tenancy thing. So yeah, this reordering is fine. And then something that Kafka gives us with their partitioning is guaranteed ordering within a partition. So I mentioned that this is sort of a performance optimization, that reordering of the things of the same color is bad, but different colors is fine. But Kafka will guarantee within the partition, so that's really just a performance optimization. So the way that we're handling this is that our normal old HTTP controller is taking in these commands, and then what it does is it tries to take a lock on a mutex for that color, basically. And so you're only ever processing a command for one tenant at a time. And then we can ensure it's idempotent by checking this committed table here to see, have we processed this command already? And then we make whatever state updates we would need based on business logic, and then insert these F events, the fact events, into the event outbox. So if the process is successful, then that's what you end up with. And then your HTTP call can return, this is successful, here's the result, et cetera, like it normally would. So basically we have API compatibility on the HTTP side, but now we have these events getting written into the Postgres table event outbox. And then unsurprisingly, other commands are coming in and other things are getting added to the table. And then the way that we manage those is that there's also this outbox worker gen server is the way we're implementing it, where it can just poll and say, hey, Postgres, how many events do I have waiting to go out for each network? And we'll see we have 2 for this red network, so we'll prioritize those just so we can keep up. But really, that's another performance optimization. It could be random. So then we lock a mutex on that network, and we publish the events, and we delete them from the outbox. And that way, we're guaranteeing at least once delivery of the events into Kafka, because we don't delete them until after they've been acknowledged by the Kafka broker. So we, if something crashes, we may publish them twice, but that's fine because we'll idempotently consume them later on the other end. And then if there's another worker operating in parallel, it'll do the same thing, but it won't be able to get that lock on the red network, so it'll lock this kind of teal network instead, do the same thing. And then unsurprisingly, there's a worker that's consuming the other one, but then if there's some other node on another machine or something that's trying to pull it, it won't have anything to lock, so it'll just wait. And Postgres gives you some good tools there, like skip locked, where you can try to grab the mutex, and if you can't, it won't just sit there and hang forever. It'll move on and get the next one. So we're using some of those fancy features. And then the next step, so after we have that event outbox, we want to be able to start consuming events too. So we'll reapply this pattern to become event-driven on our inputs, but not quite event-sourced, because you might notice that we're just deleting the events after they're written out into Kafka. So the events are not really the source of truth quite yet. That's like another further optimization down the road. But the goal is that we have these Kafka events incoming as well with commands on them. And same story here, they're partitioned and really only the order matters by the network. But the architecture is that the service will have this consumer group supervisor that manages the process for each of the partitions. And the Kafka library manages making sure that each of your nodes own all of the partitions that are in that topic, which is useful if you have multiple nodes. You want to make sure really only one of them is processing each partition. And then as they receive a batch of messages, there's this supervised task that's running that will split those up into the thing we actually care about. So this is kind of a non-Kafka sub-partitioning that we actually care about as a business, so that we can process these in parallel and not be blocked by some corrupted message coming in and blocking all other customers that happen to be in that partition. So then we do the same thing we already described, where we're locking a mutex, performing the operations, committing the commands, etc. That all happens in this consumer now. And then we just pass back the results if they're successful. Assuming they're all successful, then we pass that result back to the consumer manager thing that's telling Kafka, like, okay, now you can move on to the next batch of messages, and the whole thing repeats. All that sounds super complicated, though, until you start thinking about, okay, well, how do we handle failures? Because all these things that we've been designing here are dealing with the fact that this transaction could fail for any number of reasons. And the way that you get around that is that you just keep retrying C4 command forever until either time ends or your node gets reloaded or like something crashes and you redeploy or something, because you want to guarantee that C5 never happens before C4. But if something happens in some other network, it's fine and it will just flow through. But if this basically requires manual human intervention unless it resolves itself on its own. But when this new fresh node comes up, right, due to a process crash or a timeout or whatever, we'll know that we've already committed commands, these ones down here, C1, 2, 3, and 6. But we'll have to tell Kafka that we've already consumed C2, but we can't tell it that we've already consumed C6 because we still need to reconsume C4 and 5. So that's kind of the trick there, is that basically we're using Postgres as our commit offsets, if you've ever used Kafka before, instead of actually committing them into Kafka. And the reasons for that is that maybe like you restore your Postgres database, but now it's out of sync with Kafka and you just lost all the messages in between. That would be super bad. So then the final step here is, I'm not going to try to pronounce this, but this is like the dragon eating its own tail idea, where we have an HTTP controller where it has these commands coming in, and then instead of processing them, we just write them to Kafka, and then eventually the consumer will read it back and do the actual processing. Okay, I don't have a timer on my screen, but that's it for my content, and I'm happy to chat about anybody's experiences or questions here. And feel free to find me later here in person or on any of the chat apps.
All right, we have time for questions. We have one already there, another one there. Okay.
So one question about your implementation of the Outbox pattern. There you were publishing a mutex. So this mutex is part of Kafka API, right? Or
it's not. Yeah, no. This is something that we designed. Let me see if I can find what you're talking about here.
Tuchin. Okay.
Yeah. So this processing these things here with locking the mutex on the Outbox. So this is just something that we're implementing in Elixir and Postgres and Ecto. We're using Ecto and Phoenix, just normal stuff.
Okay.
Yeah. So the way we're doing that is we have a table in Postgres that represents each network, and we just lock the row for that network. We were going to use advisory locks, but then we got surprised that you can only have a 64-bit integer as an advisory lock, and we're using UUIDs, so those are 128 bits. So surprise, don't do that.
Yeah, and one question is here: what happens if you lock the mutex, but there is a crash when publishing event?
Yeah, so it's locking it inside the transaction. So if you crash, then the transaction gets released, and then it's fine. Yeah.
Yeah, my first question was regarding this. What's the advantage of event outbox over like transactional outbox? Because you already have the worker and it is pretty similar.
What's the advantage of event outbox over transactional outbox?
Yes.
What's the event of this advantage of event-driven thing? They kind of go together. So the transactional outbox is an event outbox. It's just stored in Postgres, and then there's a worker that's pushing them into Kafka. And then the event-driven thing is kind of an event inbox to the service, if that makes sense.
Yeah, okay, I was wondering for the reason for the mutex to
Yeah.
be there.
Yeah. So the reason for the mutex is that just we have business logic that requires we only execute one command in parallel, because this is an inventory service. So we don't want to like tell one customer that they can have something and another customer can have it at the same time. We need to like do that math transactionally.
Another question, you had this library stored that that did unified all things regarding HTTP. Two question is that library used on both reading side and writing side? And the other question is, do you have a global way to handling versioning?
Yeah, so this stored client thing is an HTTP library. Stored is our company, so it's not like an open source library. Stored client's our internal HTTP client that we use. But it encodes each of the APIs that are available on each of the services, and then they all bring that in as a dependency so they can call each other using contracts, contract-based testing and validation and stuff like that to make sure that they're calling correctly. So I'm not sure if that answers the question, but it's not related to the event-driven thing. It's just the synchronous HTTP. Yeah, versioning. So versioning, it's just a hex package. It's an Elixir library. So we just don't break our APIs mostly. Like we make a new one if we want to make a breaking change, and then people can upgrade their HTTP client version whenever they need something, basically.
All right. Do you have more questions here? People. Okay. Again, the same person. Someone else? Okay, I think we do. I don't think we have questions on Hoover. So yeah, again, you.
Yeah, sorry. So still in the topic of the outbox pattern. You implemented it with Mutex, your own solution. Did you consider using change data capture for this and Debizium?
Yeah. So change data capture. I've used Kafka Connect in the past, and it works fine. Like it does the job. The issue that I've had with it is just operationally running it, because it's like another application that someone in IT operations or something needs to run it. You have to like call these REST APIs to configure it and give it secrets and tell it what to do. So I recommended that we didn't do that at Stored, because ultimately I see that as like a stepping stone towards doing this kind of thing yourself, because Kafka Connect imposes a lot of schema things on you, and like it has a lot of design stuff, and it's running a JVM. We're not really familiar with running JVMs, so there's a lot of reasons that we didn't choose to use it, but that's definitely a thing that you could use. And I would recommend it if you don't control the application code, right? Like if you're trying to interface with an Oracle database that you didn't develop, you can plug that into some kind of change data capture thing and get your data out. That would be fine.
All right. I think we're done. Thank you again. Another round of applause.
Thanks.